Hi, today we're going to complete a warm-up. You'll be doing that with your partner, and then after that you will go through at your own pace without your partner while I go over the 6.2 notes. I'll also show you an optional video that you can watch about integrating. I'll give you an assignment. Hopefully you'll be able to start working on that in class. And then don't forget that yesterday you got an AP question that's due today. If you need time to work on it, you can take time today to complete that. Feel free to work with other people, or if you're ready to turn it in now, you can do so now. You only need to turn in the problem that's already graphed for you, not the problem on the back that has just the equations given. Here are the problems that I would like you to talk to your partner about, and when you're ready, unpause this video. Did you get those two answers? If you're stuck on the third one, here's a hint for you, and now you can pause it again. What I'm doing in problem 3 is actually taking my answer from problem 2, because this right here is the same as the question in problem 2, so I'm taking the answer of problem 2, and the derivative of negative cosine of x plus some constant is just going to be sine of x. One thing that's interesting, did you notice in these answers compared to the original problem that the original problem had the sine of t and the answer has the sine of x? Think about how what we're doing is taking the derivative of an antiderivative. That's just going to get us right back to where we started, and yet there was a variable change. One reason that there's a variable change is because when we're taking the integral, the definite integral will have us make this substitution into what the integral of sine of t is going to be. So now I have the function written in terms of x, and then I'm asked to take the derivative with respect to x, so my final answer is going to have x in it, even though the original problem started with the sine of t. That's going to be relevant to us later on. Now we're going to look at the 6.2 notes, and this is the point where you and your partner can start working at your own pace. We're going to be talking about the second fundamental theorem of calculus, but let's first remind ourselves what the first fundamental theorem of calculus was. Take a second to think about it. Can you remember what it was? It basically said if you had a problem that was a definite integral, that if you wanted to find the value of it, after you integrate, all you have to do with those values is substitute in the upper minus the lower to get the value for the integral. And as we just saw in our last unit, that value might represent area, it could represent volume, and later this semester we'll see other things that it could represent. The second fundamental theorem of calculus is going to feel like it relates a little more to the warm-up. So what I'm going to have you do is go back to the warm-up question and take your best guess at what you think the answer to problem number 4 will be. Well, here's what I mean by problem number 4. What do you think the answer would be if I had asked you to take the derivative of this definite integral? If we use the pattern that we just had from problem 3, the derivative with respect to x, going from a constant to that variable x, but on a function that's written in terms of t, it's going to be the original function, but instead of written in terms of t, it's going to be in terms of x. Well, the second fundamental theorem of calculus says if you take the derivative, and I'll write it in a semi-general form, in this case with respect to x, on an integral from a constant to a variable of some function, that because of the fact we're talking about the derivative and an antiderivative, the integral, and those are therefore inverse functions, you're going to get right back to where you started. And your book writes this in a very similar form, but both what I wrote and your book wrote leave out some important fact. So I'm going to write down what the book says. If g of x is the integral from a variable, from a constant to a variable, then If I took the derivative of the left side, the derivative of the right side would simply be f of x. Like I said, both I and the book left out an important detail. Both this black and the green, though, are representing the general idea of the second fundamental theorem of calculus. Let's talk about what it is that we've left out. What is left out is the idea of this variable up here, when maybe it's something besides just x. Maybe it's something like 2x. Well, if we're taking the derivative, we know that the chain rule would be necessary. And this derivative, as we have it written here, doesn't apply the chain rule. It doesn't acknowledge it. So we would technically need to multiply this by the derivative of that exponent. And actually, can you think of how this whole thing would be written slightly differently if I had this 2x up here? Can you tell that you would have an f of 2 of x? Let's go through an actual example. Let's look at this example. I don't want to just integrate this. What I ultimately want to do is take the derivative with respect to x. Pause this and see if you can figure out the answer. Since I want an inverse, I'm going to get back to my original function, but now that original function is going to have x squared written in place of t instead of t. But as I said, because we're taking the derivative, that chain rule would apply, and so I would need the derivative of x squared in there, which would be 2x. So I'd probably write this as 4x to the 6th minus x squared plus 3. And maybe you would distribute the 2x and maybe you wouldn't. The reason that the second fundamental theorem of calculus is coming up is because it leads us to an integral that we haven't talked about yet. If g of x, so I'm going back to more of our book's notation right now, is the integral from 1 to x of 1 over t dt, then the derivative of the left side would be g of x, and so the derivative of the right side, see if you can apply the fundamental theorem of calculus right now, you should be getting that it's 1 over x. But really, if I were going to say that g of x is given to me, I probably wouldn't want g of x as an integral. I would want g of x as some function. And we're going to try to figure out what that function is. Let's remember that if I wanted the derivative of the natural log of u, that I would get 1 over u du dx, u prime du, however it is that you would write that. And what we're trying to do is actually integrate. So for the problem I just wrote, if I integrated the right side, that would get me back to the natural log of u plus c. So what we're actually saying is that if you integrate the right side of this and I integrate the left side, this is going to give me g of x, and the right side evidently is going to give me not natural log of u, but natural log of x plus c. However, there's one issue that's almost the correct answer. We have to consider that in this original problem, our domain was that we could have everything except 0. Let's try that again. T does not equal 0. Well, the reason I'm looking at this domain is because this is the original question, and so that's going to be determining our domain for the entire problem. The issue with this is that the domain in our answer is different. I cannot substitute in 0, all right, that's fine, but nor can I substitute in negative numbers. The domain is going to be all values larger than 0. So I need to accommodate that issue. I need my original domain to be the domain for my answer. And so the way that I can take care of that is to throw in an absolute value of x. Earlier I had said I would point out an optional video for you, and that's where this comes into play. If you go to our website, down here you see the option right, where it says 6.2 integrating 1 over x. And if you watch the first few minutes of it, it gives you a little more understanding of why you need that absolute value. It also includes a graph. So they take kind of a graphic approach of why that absolute value would be necessary. So you could watch that as well. Now keep in mind when you look at this page, yours will be a little different because these notes that I'm making right now will be posted on there. So what today has led to is a definition for the natural log. And it's probably a definition that you've never seen before. And it's going to be a math definition, not a verbal definition. And it's basically that the natural log of x is the integral from 1 to x of 1 over t dt. Which means then that if I integrate, I'm going to change the variable now, 1 over u du, so if I'm going backwards, then I would get the natural log of the absolute value of u plus c. So it leads us into an integral that's going to be pretty important. What you're going to be working on are problems that are just derivatives, so some old derivative questions, as well as some that apply the second fundamental theorem of calculus, and some problems that are integrating 1 over u du. You might need some u substitution going on in there. See how far you can get through these problems. As I wrote here, you've got some log properties that are going to be coming up. Those are problems actually where you won't really feel like you need them in every problem, but I do recommend that you practice those because when we get to problems where we do need them, it's going to be helpful to have reviewed those a little bit. So work through these problems, or maybe you need to work on that AP question a little bit, and whatever you don't finish will be your take-home homework. Good luck.